Imagine a library whose pages are made of ice. There are no shelves of paper here, no ink, no written language. Instead, the story is stored in layers of frozen snow, compressed year after year, century after century, high inside the world's glaciers. When snow falls, it carries traces of the atmosphere with it. Dust, sea salt, pollen, smoke, volcanic ash, tiny chemical signals from a world that may no longer exist. As the snow is buried and slowly turns to ice, small pockets of air can become trapped inside. They preserve samples of the atmosphere itself. A bubble sealed in a glacier may contain air from a time before the industrial age. A darker layer may record a distant volcanic eruption. The chemistry of the ice can reveal changes in temperature, precipitation, wind, and environmental conditions. An ice core is therefore more than frozen water. It is a vertical timeline. Its pages are not read with the human eye alone. Scientists use instruments to examine gases, particles, isotopes, and chemical traces preserved at different depths. Each clue tells only part of the story. Together, they allow researchers to reconstruct environments that disappeared long before modern measurements began. The deeper scientists drill, the farther they move into the past. Polar ice sheets preserve some of Earth's longest climate records, but mountain glaciers tell different stories. They can preserve regional evidence from the Alps, the Andes, Central Asia, and other high places where human history and climate have met. These records are fragile. A glacier does not need to vanish completely for part of its archive to be damaged. As warming alters the ice, information stored in its layers may become harder to recover. And once a glacier disappears, no laboratory can recreate the original sequence of snow, dust, and ancient air that accumulated there. Digital records cannot replace a sample that was never collected. A photograph cannot preserve the atmosphere trapped inside a bubble, and a written report cannot answer a question that science has not yet learned to ask. That is why scientists have begun doing something that sounds almost impossible. They are removing pieces of endangered glaciers and carrying them to Antarctica. Not to study all of them today, but to preserve them for scientists who have not yet been born. Recovering an ice core begins far from any ordinary laboratory. Out here, teams travel to high mountains carrying drills, generators, protective clothing, and insulated containers. The weather can change quickly. The air is thin. The equipment has to operate in cold, in wind, and on difficult terrain. The drill descends into the glacier, then slowly returns with a cylinder of ice. A typical section is about 1 meter long and 10 centimeters wide. Each piece is carefully wrapped, numbered, and documented. Scientists record its depth, its direction, and the exact place where it was collected. From that moment on, the cold chain cannot be broken. The ice has to remain frozen during the descent from the mountain, during transport across countries, inside laboratories, and eventually across oceans. Even a carefully recovered archive can be damaged if its temperature is not controlled. The Ice Memory Initiative began in 2015 with a long-term idea. Collect cores from selected glaciers that are threatened by degradation or disappearance. Analyze reference material with today's instruments, and preserve separate heritage cores for tomorrow. On several expeditions, researchers recover more than one core from the same glacier. one can be analyzed now. Its chemical composition, its isotopes, its particles, and other characteristics help create a scientific reference database. Another core can be preserved with as little disturbance as possible. That distinction matters. Data collected today can only answer questions that scientists know how to ask today. Instruments measure what they were designed to detect. Methods improve. Entire fields of research can emerge from discoveries that no one expected. So the project preserves more than measurements. It preserves the original material. A future laboratory may detect particles too small for current instruments. It may identify chemical traces that researchers today cannot interpret. It may reconstruct environmental events with a precision that now seems impossible. Raw ice preserves possibilities that a spreadsheet cannot contain. Once the sample is consumed, contaminated, or allowed to melt, those possibilities are gone. The scientists working on the mountain may never see the discoveries made from the material they save. Their role is different. They are preparing evidence for strangers in another century. There is a quiet paradox in this work. A piece of ice has to be removed from its glacier so that part of the glacier's memory can remain intact. One core may be studied now, helping science understand the present. Another may be sealed and left untouched, waiting. Not because science has nothing to ask, but because the future may ask better questions. In late 2025, the first heritage cores prepared for the new sanctuary began a journey from Europe to Antarctica. They came from two alpine glaciers connected by a common fate. One had been recovered from Col du Dôme in the Mont Blanc Massif. The other came from Grand Combin in Switzerland. For centuries, these glaciers had been quietly recording the history of the atmosphere. Snowfall after snowfall, layer after layer, year after year. The ice had already survived snowfall, burial, compression, drilling, and years of protected storage. Now, it had to survive another test. A journey of more than 50 days aboard the Italian research vessel Laura Bassi. Throughout the voyage, the cores had to remain frozen, guarded against even the slightest thaw. After crossing the ocean, they still had to travel inland, away from the Antarctic coast and toward the high plateau. Their destination was Concordia Station, a French-Italian research base in one of the most remote regions on Earth. Here, human presence feels temporary, but the ice is meant to endure. Concordia stands approximately 3,233 meters above sea level. The air is thin. The landscape is almost entirely white. And during much of the year, the natural temperature is far below anything required by an ordinary industrial freezer. Near the station, engineers created a sanctuary inside compacted snow. The chamber is approximately 35 meters long, 5 meters high, and 5 meters wide. It lies approximately 9 meters below the surface. There are no conventional refrigeration machines keeping the archive alive. The Antarctic environment does the work. Inside, the temperature remains close to minus 52 degrees Celsius throughout the year. The storage is passive, using natural cold instead of depending on a continuous supply of electricity. That matters because ordinary freezers can fail, power can be interrupted, mechanical systems age, institutions and governments can change. The snow cave reduces those risks by placing the archive inside an environment that is naturally colder than most artificial storage facilities. In this way, The sanctuary is both simple and profound. On January 14, 2026, the Ice Memory Sanctuary was officially inaugurated. The first 2 heritage cores were carried inside and placed in the frozen chamber. It was a small beginning. 2 collections of ice in a room designed to receive many more. But symbolically, something important had changed. Here, mountain ice was being treated not only as a research sample belonging to the present, it was being protected as a scientific inheritance. A fragment of a disappearing landscape had been given a new destination. Not a museum for visitors, but a working archive for the future. An archive built in cold and silence, holding stories that can only be heard when the ice is carefully brought back to light. The sanctuary is not meant to belong to one country, one laboratory, or one generation. Its purpose is to preserve a shared scientific resource for the whole planet. Access is intended to depend on scientific merit and on transparent ethical criteria, while an international system of governance slowly develops around the archive. This idea gently changes the meaning of ownership. A glacier may stand inside one nation's borders. A research team may drill the core. A laboratory may protect it for years. But the atmosphere trapped inside that ice was never confined by a border. The winds crossed continents. Volcanic particles traveled through the sky. Dust rose from distant deserts. Snow recorded a planet whose systems were connected long before humans created maps. A century from now, a researcher may enter a cold laboratory and receive a small section from one of these cores. That scientist may use an instrument that does not yet exist. They may study a gas we do not currently measure. They may identify a biological or chemical signal we do not yet recognize. They may discover a connection between the atmosphere, the environment, and human history that we have not imagined. The information may have been inside the ice all along. What was missing was the technology capable of seeing it. That future researcher may also know that the glacier from which the sample came has changed beyond recognition, or disappeared. The sanctuary cannot stop that loss. It cannot replace the living glacier. It cannot restore the mountain landscape, and it cannot solve the climate crisis by itself. Preservation is not the same as protection, but when protection comes too late, preservation can keep evidence from vanishing with the place that created it. That is the deeper meaning of ice memory. It is an admission that knowledge can be lost, and it is a quiet refusal to let every trace disappear without an attempt to save it. The ice was formed before we were born. It recorded the sky without knowing that one day we would need its testimony. Now, fragments of that memory are being carried to the coldest archive on Earth, for people whose names we will never know. The glacier may disappear, the mountain may lose its ice, but if the memory survives, the questions do not have to disappear with it.